There comes a point in every discipline where assumptions harden into facts, not because they are true, but because to question them would shatter the foundation upon which an entire field stands. People cling to these falsehoods, not out of ignorance, but out of necessity, because to challenge them would risk making a fool of oneself. Nowhere is this more evident than in meteorology, where one of the most stupefying myths persists, the myth that steam, in its gaseous form, can exist in the open atmosphere. This belief is nearly universal among meteorologists, and yet, remarkably, not a single one could point to a definitive experiment proving its validity. What little evidence we do have suggests the opposite, but this inconvenient truth has become a taboo, an unspoken rule reinforced by the very experts who should be questioning it. For the majority of meteorologists, this myth is of little consequence, as their work revolves around synoptic charts and computer models, cold fronts and warm fronts rendered as simple lines on a screen. In their day-to-day duties, the concept of atmospheric steam never enters the conversation. But for a small subset of meteorologists, those who wrestle with the complex and unpredictable nature of severe weather, this myth casts a long shadow. These are the storm chasers of science, the ones tasked with understanding the forces behind tornadoes, hurricanes, and other violent atmospheric phenomena. And yet, their progress is stunted, their theories hollow. For them, this myth is more than a harmless fallacy, it is an intellectual dead end, one that leaves them grasping for answers in a field that should be teeming with possibilities. In this corner of meteorology, to even question the validity of steam in the atmosphere is to risk ostracism. And so, the myth lives on, not because it holds any scientific merit, but because it keeps them from looking like fools. Beneath the surface of meteorology, there exists a subtle game of evasion, a dance of words that hides the uncomfortable truth about convection. Meteorologists don't openly discuss steam in the atmosphere. Instead, they speak of convection, a process they understand through the lens of Avogadro's law. But when pressed to explain the underlying assumptions, they reluctantly reveal their belief in the existence of monomolecular HO, steam, in their models. This, they say, is the unseen player in the dance of convection. Yet, ask them how water molecules could possibly remain monomolecular at temperatures far below the boiling point, and that's when the evasion begins. The conversation shifts, becomes defensive, and emotions flare. This subject, seemingly innocuous, runs deeper than one might expect. Suggest that steam cannot persist in the atmosphere, or point to the lack of experimental evidence supporting its role, and you may find yourself branded a fool, or worse, a liar. The reaction is visceral, akin to the debate surrounding carbon dioxide forcing in climatology. But unlike the politically charged arguments over carbon dioxide and global warming, this particular myth lacks an ideological battleground. There are no political factions squaring off, no grand narratives about impending global catastrophe. It simply exists, unchallenged and strangely unexamined, despite the very real catastrophic forces at play in severe weather. Tornadoes, hurricanes, these phenomena don't care for politics. Their destructive power is undeniable, and yet the models built to explain them are quietly grounded in an assumption that steam plays a part, an assumption few are willing to scrutinize. As we dive deeper into the myth of steam-based convection, the story becomes even stranger, especially when we consider just how resilient this theory has been, despite its repeated failure to predict critical atmospheric phenomena. Like a relic from a bygone era, it persists, unchallenged, while new discoveries pile up, each one revealing cracks in the old model. There have been three major waves of evidence, largely spurred by advancements in aviation, that should have shaken the very foundation of this myth. And yet, the theory remains immovable. The first wave came with a shocking discovery: extreme turbulence at the top of thunderstorms. For decades, meteorologists assumed that as water vapor rose into the colder upper reaches of the atmosphere, it would condense, become denser, and lose its buoyant energy. Thunderstorms, viewed from the ground, appeared to have fluffy, innocuous tops, benign in appearance. But the reality, as revealed by pilots who dared to venture into these storms, was far more terrifying. Consider the testimony of Joe Olson, a young pilot who, on a solo flight over Texas, found himself swallowed by a thunderstorm. Entering the cloud felt like hitting a wall, he recounted. Suddenly, everything was white. Rain came from every direction, and the wind howled. Vertical wind shears rendered the instruments useless, the gauges bounced wildly, and you were flying by instinct, in a disorienting blur of glowing white light. This was no peaceful cloud. It was a chaotic, violent force, tearing at the wings of his plane, with winds over 200 miles per hour battering the craft. Pilots soon learned to fear these storm tops, and for good reason. Some storms were so powerful, they punched through the tropopause into the stratosphere, hurling air over 60,000 feet into the sky. Yet, despite this overwhelming evidence of violent activity high above the Earth, the steam-based convection model remained largely unshaken. One might think that the ferocity of these storms would have inspired meteorologists to reconsider the processes at play, to open their minds to forces beyond mere convection. But instead, the myth endured. The second wave of evidence came during and after World War II, with the discovery of the jet streams, fast-flowing rivers of air that snake through the upper atmosphere. Pilots flying high above the Earth began to notice these invisible highways of wind, capable of carrying them vast distances or battering them with unexpected turbulence. Jet streams, as we now know, flow near the boundary between the troposphere and stratosphere, but their paths are anything but straight. They meander, split, and even flow in reverse. They are wild, untamable forces of nature. Yet, as with the turbulence at the top of thunderstorms, the jet streams weren't predicted, or even hinted at, by the steam-based convection model. This monumental discovery should have been a wake-up call, a signal to meteorologists that their model was incomplete. But, once again, the myth persisted, and alternative models were never seriously considered. The final wave of evidence struck in the form of clear air turbulence, CAT, a particularly dangerous and unpredictable form of turbulence that occurs without any visible warning. Pilots, trained to look for cumulus clouds as signs of rough air, quickly learned that CAT could strike even in cloudless skies. Invisible to the eye, this turbulence poses a serious threat to aircraft, often resulting in injuries because there's no time to brace for impact. CAT is most frequently encountered near the jet streams, at altitudes where the troposphere meets the tropopause, a zone where atmospheric forces collide in ways we are still trying to fully understand. And yet, despite its dangerous nature, clear air turbulence was yet another phenomenon that the steam-based convection model utterly failed to predict. No steam-based theory could account for these powerful, unseen forces. And still, despite this mounting evidence, the model has remained largely unquestioned. These three waves of discovery, each one revealing a new and critical piece of the atmospheric puzzle, should have forced a reckoning in meteorology. But instead, the field remains wedded to a model that cannot explain the full complexity of storms. As we continue to explore these phenomena, it's clear that something fundamental is missing from the theory of storms, a missing link that has yet to be discovered. The failure of the steam-based convection model to predict key meteorological phenomena should have raised alarms, but the response from the meteorological community has been surprisingly quiet. Instead of reassessing the theory, many have chosen to sidestep the evidence and continue presenting their models as if nothing were amiss. One can't help but wonder why this persists when the shortcomings of the model are increasingly clear. Rather than acknowledging the gaps, they often bury the more problematic aspects, such as the notion of steam, within more familiar concepts like convection. Dissent, meanwhile, is met with deflection or outright dismissal. The crux of the issue lies in how meteorologists explain one of the most basic processes in the atmosphere: how water gets into the sky. The pervasiveness of HO at all altitudes, and its presence in every storm, is undeniable. And while the phases of water, ice, liquid, and gas are well understood, explaining how moisture gets beyond a few kilometers into the upper troposphere poses a greater challenge. This is where conventional thinking runs into trouble. It would seem that steam, as the gas phase of water, is the only logical explanation for how moist air could rise above drier air, powered by buoyancy. And yet, this explanation doesn't hold. The truth is, steam cannot exist under the conditions found in the upper atmosphere. The idea that buoyancy is the only force responsible for lifting moist air in storms is flawed. In fact, the three key phenomena discussed earlier, the turbulence at the tops of thunderstorms, jet streams, and clear air turbulence, suggest the presence of another force altogether, one that can explain the rapid rise of moisture to altitudes well beyond what steam or buoyancy alone could achieve. In an upcoming analysis, we'll unravel how this force works, tracing it from clear air turbulence all the way down to the moist air near the surface, offering a more complete and accurate picture of how storms really operate, without invoking steam at all. So, what is the mistake meteorologists have been making? What conceptual blind spot has left their theories incomplete? As we've explored, the assumptions that have guided meteorological theory have been based on the idea that HO exists only in three phases: ice, liquid, and gaseous steam. These assumptions were understandable for their time, as meteorologists simply didn't have the tools or insights to recognize the existence of a fourth phase of water, plasma. This plasma, invisible and unrecognized, holds the structural capabilities that traditional models have overlooked, and it is this overlooked force that can explain the true dynamics of atmospheric uplift. The plasma phase of water is not a simple, ethereal state. It is a dynamic and structural force, capable of shaping the very behavior of storms. It provides the missing link, the power that elevates moisture into the upper atmosphere with a force that goes beyond mere buoyancy. This realization changes everything. It is not just an adjustment to existing models, it is a fundamental shift in our understanding of the atmosphere itself. And yet, this discovery doesn't require meteorologists to abandon their work or surrender their dignity. Quite the opposite, this plasma phase adds depth and clarity to their understanding, allowing them to finally explain the powerful, often violent, forces of storms in a way that aligns with the evidence, not against it. In the chapters to come, we will dive deeper into this fourth phase of water, tracing its role in the atmosphere and uncovering how it might not only reshape meteorology but also revolutionize our understanding of severe weather. The journey to this discovery begins with recognizing the limits of past assumptions and breaking free of them.